Here is the agenda for today. First, I will start by introducing our expert speakers. Next, Shaun will lead the first session, sharing his insights. Then, following that, Mithra will present the second session. Lastly, I'll wrap up and close our webinar. Let's kicking off with inside, meet our experts. For our first session speaker, Shaun Yang is a chartered professional engineer with over 12 years of experience in civil and structural engineering design and delivery. He has contributed extensively to all stages of project lifecycle, including feasibility assessments, detailed design, construction, and maintenance. Shaun specialized in designing pre-stressed concrete and steel bridge, and he served as a lead designer for Australia's longest and largest single-span tier roof bridge beams. Currently, he is a senior engineer and structure lead for the level crossing removal projects at Aurecon, managing the detailed design of complex road over rail bridges. Since 2022, Shaun has also been sharing his expertise as a guest lecturer for the Master of Civil Engineering program at the University of Melbourne. Now let's hand it over to Shaun so he can share his expertise and kick off our first session.
Thanks, Yang. Let me know if you can hear.
Yes, we can hear you.
All right, I'll just quickly share my screen. So let's make a start. Thanks for the introduction, and I'll make a start on the presentation today. So hi, everyone. My name is Shaun. I'm a senior engineer from Aurecon's Bridge and Civil Structures team here in Melbourne. So today I'm going to talk about the level crossing removal project here in Victoria, which I've been working as the structures discipline lead for the last 12 months. And today's presentation will cover some interesting design topics that we encountered in general, as well as structural design for the Ferris and Hopkins Bridge and associated deflection wall using MIDAS. So I always like to, give everyone a bit of a breakdown on the what's involved in the presentation. So I'll quickly go through a bit of a self-introduction. Then we'll have a snapshot of the level crossing removal project, Ferris and Hopkins site. And then I'll spend most of my time talking about modeling, analysis, optimization using MIDAS, so circulating around bridge design and structural detailing. And then I'll quickly go through some of the interesting sustainability initiatives and how do we adopt a sustainability in structural design. And lastly, I want to share some of the lessons learned and potential collaborations ahead. So a bit about myself. I'll just use my cursors here. So I actually started in construction. So my first job was as a site engineer up in the Kimberley's region in Western Australia. I spent 12 months on site doing 11 days on, 3 days off roster. So I was directly managed 12 plus operators on site, including excavator, water cart, roller, and so I was involved in road construction, widening, bridge modification, repairing, and construction. So then I get to rotate through a list of interesting infrastructure technical branches, including waterways, bridge structures, both timber and concrete and steel bridges. I also did some work in the civil road alignment design, transport modeling, planning, and metropolitan project development. And then I also get exposure in asset management and maintenance. So after I completed my graduate program, I then started working on geotechnical design for road formation and bridge foundations. And I also carried out laboratory testings for a series of asphalt tests as well as concrete coring test on the bridge deck. So I'm accredited structures designer checker in multiple rail authorities here in Victoria, and I'm also a accredited level 2 detailed inspector by ARRB. Like Yang mentioned, in 2022, given my extensive experience in various aspects of infrastructural engineering, I was honored to be invited by the University of Melbourne and present guest lectures to students enrolled in concrete design and construction engineering. It has been an amazing journey so far, and this year I was even invited to participate in preparation of assignments and exams for the final year students enrolled in Master of Civil Engineering. So here are some key projects that I worked on in the past. I'm not going to go through them one by one. I just want to quickly go through some of the interesting aspects throughout my 12 years plus experience. So the first picture on the right is the Metronet Ranford Road Bridge, which was known to be the longest single span simply supported precast pre-stressed concrete tier-off bridge beam ever built in Australia. So the bridge consists of 10 tier-off girders, and each weighs about 200 tons. 3 heaviest crane was utilized to assist with the lifting of the beam. And it was one of the amazing experience that I think during my last 12 years career that I get to participate in tender design and then detail design and finish the construction support for a multi-billion-dollar project. And on the right-hand side, it's the Armadale Access Alliance. It's underpass structures. I just want to share with everyone that, as a structural designer, we don't just, dealing with boring reinforcement details or, big chunky of reinforced concrete and steel. We also get to work with a whole list of teams that contributes to the architectural design, landscape detailing, and as part of our structural deliverable, we get to actually work with the urban designers and actually provide making positive contributions to the local community. And the third picture here is the Elliott Place footbridge over the rail. So this is another interesting project that I did as part of the Metronet design. The bridge is 40 meters single span over the existing rail and future-proofing the future rails, passengers rail. The interesting bit is this project was actually designed for 120 years. For steel truss bridge to achieve 120 years maintenance-free period over the rail was quite challenging. And for a 40-meter long span, we had to consider double dipping of the hot dip galvanized layer with the local dipping pool and make the design to achieve the required design life. On the right-hand side here is the level crossing removal project here in Victoria, the Fitzgerald Road site, which is a 2-span continuous bridge at the Central Pier. And this job has already been completed in 2022 and open to traffic. The last one I want to share here is the Melbourne Airport elevated roadway. So as I progress, into the design management role further, I start managing a group of engineers. So in 2022, we delivered the Melbourne Airport elevated roadway detail design of Bridge 03, which ties into the International Airport car park with bifurcations to the level 2 and level 3. So overall, I have working experience in a whole list of bridge and civil structures, including miscellaneous structures like steel signage, culverts, deflection walls, underpass, and also tunnel and underground stations. I also do existing bridge inspections and also the load rating assessments for both road and rail bridges. Okay, so enough about me. Let's talk about the project. So level crossing removal projects Ferris and Hopkins. To start with, just to give a bit of general background, what is level crossing and what is level crossing removal? So basically, level crossing means the road alignment and the rail alignment is intercepting each other. So one needs to give way to another from time to time. The removal of the level crossing basically is the grade separation, the simple words. So how does it work? It's basically a redesign, reconstruction of the horizontal and vertical alignments of the rail and the road with supporting bridge and earth retaining structures to support the elevated roadway or the railway. Why do we do it? It's very simple. There are a whole list of reasons, but the main reason here is to improve safety and eliminate collisions. So the two photos here happened in the past in Victoria. The ongoing road traffic collide with the train. And the photos on the right just give you a very quick example, snapshot of how it's been done. So this is the Robinson Road side. Previously the level crossing had the rail, the V-line train line running, intercepting with the road traffic. So Aurecon was the structural designer of this project, and we basically lowered the roadway under the ongoing train line, and then eliminate the potential collision between the two alignments. And this project has been completed in 2022 and open to traffic. Next one. So where are Ferris and Hopkins sites? So if you can have a look, this is the Melbourne CBD. We are northwest of the Melbourne CBD. And this is the V-line train road from Melbourne to Melton, Ballarat. So as we travel away from the city, we will then encounter the two level crossing, which is Hopkins and Ferris. If you have a quick look at the Big Build Victoria map, it will actually show you the ones that has been removed, which is the Fitz and the Rob sites before we get to Hopkins and Ferris. So Aurecon has delivered the design and construction support for Fitz and Rob in 2022 and 2023, and continue the design work for Hopkins and Ferris. Overall, when we start working on the design, the detailed design, we'll start with the concept, and then we'll start proposing and evaluate multiple road alignments, rail alignments to suit the stakeholders' needs. So here we've got some existing level crossing photos that we've taken on site, and the middle ones is the proposed road alignment. And on the right-hand side, some really amazing 3D images produced by the Metropolitan Roads Program Alliance coordination team. So basically, the design team will propose the alignment, and then we'll come up with the 3D images, and then we'll go out there and consult with the community, the council, DTP, and the end road users. So each site can be slightly different due to its road and rail boundaries. As you can see here, for Hopkins Road, the new alignment is actually significantly away from its existing alignment. And this is proposed to accommodate the future traffic growth and future-proofing the duplication of the bridge and the road. Whereas for Ferris, due to the constrained site condition, the new bridge is pretty much adjacent to its existing road alignment. Okay, so we talked about external consultation. So let's talk a little bit more about internally. As a design team, what do we do? So bridge design is not just about provide a span from point A to point B. We have to do a lot of the design interface to make sure that we meet all the required geometric requirements, sustainability targets, durability requirements, etc. So just going through the circles here, we some of the key interface that we need to carry out basically from day-to-day coordination is the civil and rail alignment, utilities, geotechnical, pavement drainage, lighting, sustainability, earthing bonding. That's a very interesting one that we not only just worry about the anti-throw screen, but we also provide future proofing for the electrification for 1500 volts DC and 25,000 AC. And then we do clash detections at every stage of our design. We have to do system engineering. And then we also have collision protection assessment and workshop with our client. Then we also need to participate in the architectural and landscape design. Like I mentioned, the bridge is all about functionality, but also we need to make sure that the aesthetic appearance of the bridge, ties into the local community and sort of ties into the local culture. So this is just a bit of snapshot of what we need to do, between disciplines. And sometimes it's a joint effort, not just, one-way communication. We actually have to go into each other's area and start, deciding how do we actually compensate each other and make things to work. So on the left-hand side, we have the Hopkins Bridge. So Hopkins Bridge is 3-span simply supported with a total length of 80.5 meter with a skew angle of 38.6 degree. On the right-hand side here, we have the Ferris Road Bridge. The total length of the bridge is 50.1 meter. It's 2-span continuous at the central pier and integral at the abutment via institute concrete stitch. So we do a lot of the 3D image to make sure that the stakeholder understands what we are trying to present. And we also have an ongoing 3D revistal model to provide clash detection for both bridges. Due to time constraint, I won't be able to actually go through all aspects of the design. So I want to share some interesting design topic that we encountered during the detailed design. So I like to talk about the case study of how do we actually determine the bridge alignment, horizontal and vertically. So the bridge alignment takes consideration a whole lot of geometric constraints, including surfaces, road alignment, future proofing, and for road as well as rail. For a bridge we have in Hopkins Road, we need to make sure that we're not only accommodating the existing railway track, which is shown in blue here. We also need to make sure that the future railway tracks can be accommodated. And then we also need to accommodate the future SUP as well as the future connector console roads. So this is how we form up the elevation of the bridge or to achieve the horizontal clearance for the bridge. And then let's talk about the vertical clearance. So, every 300 mils, we need to consider how do we actually lift up the road formation, how do we actually tie it into the road. As you can see from the plan here, the road formation, as it goes further close to the bridge, the road formation gets lifted up with embankments, slopes on either side of the road. So we want to make sure that the vertical clearance accommodates the rail envelope as well as when there's a transient live moving load on the bridge, it doesn't encroach into the clearance. So let's take into a bit of a 3D geometry of the bridge itself. So longitudinally, I'll just quickly go back. Longitudinally, we know the bridge has a longitudinal one-way fall. Transversely, the crossfall of the road surface and the shared user path, the SUP surface, basically indicates that the lowest point of the superstructure is between beam number 2 and beam number 3 from the left. So now we understand longitudinally where is the bottleneck, and we understand transversely where is the lowest point. So this is our governing location to set out the bridge. And then this information then needs to communicate with our civil and rail team. So from Civil's perspective, the civil design team will provide us a design string in Civil 3D, which then shows the reference points at the top of the asphalt adjacent to the curb. And the rail will basically provide us the top of the railway track, and then and also the required rail clearance envelope. Then it is up to the structures team to then assess what is actually happening between the two. So the structures team needs to actually, come up with the physical depths of the superstructure depths. And then we also need to understand the behavior of the pre-stressing girder in the composite with the deck slab. And then how does it actually behave in the long term due to concrete creep and shrinkage and pre-stressing losses in tandem? And then when there is live traffic on the bridge, how much does it actually sag? And then what happens, when the substructure settles in the long term, and how much construction tolerance that we need to agree between rail and civil team. So this basically gives you guys a bit of a taste, in terms of design interface between internal design teams. Now, I'd like to go even further into the bridge design. So the blue was the blue colored dash line. Oops, sorry. So the blue colored dash line is the external consultation. The green color is what we just talked about, the internal disciplinary coordination. Now, within the black line, we are talking about the bridge design. So I like to think bridge design consists of 3 parts: the superstructure, the substructure, miscellaneous elements. And the 3 components gets built by anticipated construction staging, workshopped with our delivery team from MRPA. So the structural bridge design needs to meet all the project requirement scope and specification, and all the requirement in AS5100, which is our bridge code. The structural design considers the ultimate limit state, service limit state assessments, fire effects, and fatigue assessments, and so on. So, a lot of people may be asking, we as a designer, there are many commercial programs out there, and why do we choose MIDAS? And just about, you start familiar with how to use MIDAS, and then MIDAS has a new fancy program called the MIDAS NX. Why do we continue changing it? So I like to basically share from an end user's perspective. MIDAS NX, it's pretty much MIDAS Civil plus API functions. So any MIDAS Civil models can be operated in MIDAS NX, but API functions can only be operated in MIDAS Civil NX. But MIDAS Civil NX, API functions are here to improve efficiency where required, and they are optional. Okay, so before we get into the modeling using MIDAS, I just want to highlight that this presentation is not about how to use MIDAS 1001. I'm here to provide some insights into how MIDAS program can benefit our day-to-day bridge design as a MIDAS end user. I do not believe that I can do a better job than MIDAS support team or the MIDAS IT team, because when it comes to teaching beginners how to use MIDAS program, there are many useful tutorials, and I do not wish to embarrass myself here, and I do not wish to repeat the steps that you can easily find online. My philosophy is always that as a design practitioner, we learn on on-job training and trying to solve the problem by picking up the design skills. So therefore, I want to spend most of the time focusing on the end results. How do we actually implement some of the features that's available in MIDAS to help improve our design efficiency and accuracy? So first of all, just like start at every single job, when you get into a new design project, I always make sure that my team of engineers is aware that MIDAS is a design program here to help us, but the designers or the end users should be responsible for the accuracy of the model they produce in MIDAS. So we can't simply blame a black box that we're not sure, and then start thinking that we'll click the button and, you know, garbage in, garbage out, and we get the job done. So that's always not the case. We want to make sure that we assess the output by way of internal verification and calibration by the design team. So we have done a whole lot of verification, and here is an example summary here. We have checked hand calculations of the dead load, superimposed the dead load, earthquake calculation, anticipated abutment deflection with the help of geotechnical model, which will be shared later on. So overall, we are pretty happy with our hand calculation, and which aligned with the MIDAS output quite closely. And on the right-hand side, it's one of the key features that MIDAS offer for the moving load tracer. So, you know, as a beginner, when you first start design a bridge, you want to understand where is the governing load location. Does this load pattern looks correct? So MIDAS offers this feature to actually pick the element that you're interested in and provide the corresponding load patterns for designers to review and evaluate. I'll go a bit more into this function just to talk about how does MIDAS differentiate itself in this area. So a bit more about the calibration that we did between structural models and geotechnical models. So obviously the design actions and deflections that we have basically checked between the geotechnical plexus model and the MIDAS 3D models. So on the left-hand side, we have got the construction staging showing the substructures only for Hopkins Bridge, and we have got the associate Hopkins plexus model to verify the design actions in the piles, in the blade wall, and also the deflection. On the right-hand side, we have a bit more complicated structures here. It's a two-span continuous and integral bridge. So again, we have got the Plexus 2D model to calibrate the soil behavior and then feeds back into our 3D model. Okay, so I mentioned that we're going to talk about the moving load tracer. So MIDAS offers this moving load tracer, but in addition to a common, you know, feature that you can pretty much find in some of other programs, MIDAS also, you know, help us to fast track how do we actually fit the critical or the corresponding load pattern into the next stage of our design. So back in the days that when we carry out the design of a bridge superstructure and the bridge substructure, when the bridge is simply supported on bearing and then supported on substructures, we may choose different program to carry out our grillage model. Then we record the reactions, and then we manually input that into our 3D substructure model. It is time consuming. It is, you know, potential errors due to, you know, human errors. And so MIDAS is basically, you know, helped us out and basically creates this individual or batch load conversion function. So as soon as you identify the critical load pattern that you are interested in, you can pretty much convert that into an ACT command in text file and then re-import it back into MIDAS as an individual load. So this was a huge time saving for our design program on this job, because due to the tight program, we were actually running the structural design and detailing for superstructure and substructure simultaneously. So if every time the substructure detailing team needs to run the model and has to include all the moving loads on the superstructure, it's going to be significantly more time consuming. So we were able to use this feature, batch convert a whole list of critical loads that's causing the critical actions in the substructure and fast track the structural detailing and design of the substructures to meet the design program. Another very powerful feature of MIDAS is the construction stage. I'm sure, you know, everybody is familiar with this function here. So I'm not going to go through any steps of how to set it up. I just want to quickly show some of the main steps that we actually use in our design. So starting on the right here, the first one is the substructures only. Using this stage here, we can introduce sub-stage to look at how much backfill and how can we backfill the behind the abutment wall and see what's the actual allowable deflection, what's the actual design deflection versus the allowable deflection. So we were able to actually workshop with our construction team and come up with the most optimized construction sequence. The next one is when the pre-stressed beam were lifted in place, simply supported on the bearing. We'll then have the wet deck concrete loadings here. Again, because you get to separate the stages and you understand the support conditions, we were then able to accurately reflect the wet deck concrete loading to align with our actual deck casting sequence. The deck casting sequence needs to comply with the DTP specification 610 with a maximum of casting sequence length to be 25 meters. We also workshop with our construction team and make sure that the joints or between the stage 1 and stage 2 achieves the minimum offset requirement from the existing railway track. And that was then captured in the 3D model. So some of the interesting findings that we got from the 3D model. So first of all, I want to mention that because it's a 3D model, it sort of helps us to look at how the structure that is behaving in multiple dimension instead of just a 2D model that we're showing on the left-hand side here. So one of the main findings that we got was that because of the heavy skew with 8 to 9 meters of backfill at the back and the significant cantilever abutment wing wall that is constructed monolithically with the abutment wall here, the soil pressure with the load combinations specified in AS 5100 Part 2, it's actually causing the push and pull effect and causing significant tension in the piles at the back end here. So this would never be clearly defined if we simply had a 2D element modeled in a 2D plane. So that was one of the very critical benefit that we got using a 3D model in MIDAS. And in addition, like I mentioned, that we also need to assess the anticipated deflection of the abutment wall and make sure that the deflection meets the DTP BTN 023 foundation and soil supporting structures. So the next one is moving on to the Ferris Bridge. So Ferris Bridge is continuous two-span bridge, continuous at the central pier, integral at the bridge abutments. So the construction staging was, again, helped us to understand the backfill sequence and the limitations that we need to workshop with the construction team. Then we again look at the 3D behavior of the bridge due to the skew, the integral abutments, the continuity at the central pier. Now, this is not optional because as per the DTP BTN 010 integral or the semi-integral bridges, we actually need to investigate the creep, shrinkage, and differential temperature settlement, and also earth pressures in stages, and making sure that we cover both the short-term and as well as the long-term effects for an integral bridge, which is why we modeled the 3D models for Ferris Bridge as well. Some of the interesting findings based on the 3D model. So first of all, I'd like to mention that if today, without the construction sequence, we just proceed with our grillage model with a frame action, then the frame is going to recognize the composite behavior from day one, which means that the weight of the deck slab will be supported continuously. What does it actually do is then it will reduce the actual sag bending and creates a unrealistic hot bending at the central pier as well as the abutments. So by having the construction stage, we were able to actually specify the support condition during its wet deck concrete stage 1 pull, and then make it composite, partially composite, and then continue our stage 2 construction with the deck and the stitch pool at the pier as well as the abutment. So as we all know, Super T girders, it's great with resisting sag bending moments because we can put more and more strands, multiple rows of the strands at the bottom flange of the Super T. But the Super T composite section is weak or not as efficient in resisting hogging moments. So this is one of the typical challenge that we have when we have a continuous breach. A lot of the reinforcements needs to be squeezed into a very narrow 200 mils deck slab, which is this area here. So by having a clear construction staging and a clear wet deck sequence, we were able to find out the actual realistic sagging moment, which made sure that the Super T were not under design for the misbend sagging. And then we're also able to detail and provide a very efficient structural detailing for the deck slab at the critical hogging zones at the pier as well at the abutment. And this breach also was assessed in close detail for fatigue assessment because there is a rigid moment transfer at the pier as well as the abutment with multiple sectional property changed as we progress for throughout this support location here. And we found that the fatigue assessment basically governed multiple locations at the bridge pier as well as the abutments. Okay, so the next big topic I want to talk about is the stress at transfer. So this is again a very common topic when we are detailing or design the pre-stressed Super T girders here in Australia. So stress at transfer, basically, we need to make sure that we're not putting too much strength into our bottom flange, and we need to make sure that compressive strength complies with AS5100 with reduction factor, and we also need to make sure the tension, the tensile strength also meets the crack control requirements. So the MIDAS basically offers a one-stop shop within the 3D model. It allows us to provide the sectional property, including reinforcement layers. And it also allows us to put in strength profile, including the bonding lengths. So it allows us to look at everything in 3D, longitudinally as well as transversely. So the example on the right-hand side here is the stress at transfer profile for tension and compression of one of the beams taken from the Ferris breach. Just a bit of a lessons learned or an important step is in MIDAS, the pre-stress force is recognized as a load case. So after you have established your strength profile, you need to make sure that you apply that as a load case. Okay, so look, this is what I always talk to my teams, the junior engineers, is we can't, MIDAS needs to earn our trust, just like any program. So we need to carry out our own verification to satisfy ourselves that the output generated by MIDAS is satisfactory to the design team. So stress at transfer is not difficult to verify. We just have to consider the three main components: the axial compression due to the tendon, the moment, the clockwise moment due to the tendon force, and the eccentricity to the girder. And we also need to consider the self-weight of the girder. And on top of that, we need to make sure that we calculate our stress development and the transmission lengths as per 5100, pre-stress losses, short-term and long-term as per 5100, and align with our MIDAS input, and also considers the modular ratio transformed between concrete element to steel elements in the calculation of the neutral axis. And again, very lastly, to everything above this point, we will get a approximate stress with assessments of elastic deformation losses, we will get the results pretty closely aligned with what we can model in MIDAS. So this is just to assume that compression is taken to be positive and tension is negative. We can quickly run these calculations in our own Excel spreadsheets to verify the output. The last topic I want to sort of mention about something powerful in MIDAS is the beam hog estimation. So we talked about this diagram here. So as structures engineer, we need to understand the behavior of a pre-stressed beam, throughout its serviceable life. At the start when it's only girded only, and then a composite with the deck slab as a composite behavior. Basically, how do we then investigate the behavior here? I have now listed multiple stages. Basically, start documenting when the girders gets manufactured, stored on the garage, the storage yard, and then lifted on site, lifted into place on the bearing or stitched with the continuous structure. And I also listed out how it's actually relevant to our design. So for example, at stage 2.2, when the girder gets lifted in onto the elastomeric bearing, then we need to make sure that the set out of our bearing level and the pedestral levels have been checked and meeting the design intent. Then we also have the stage 3.3. So deck slab achieves the strength and achieves a full composite section. So when you calculate the beam, the superstructure deflection, you need to consider the composite section. And then lastly, in the long term, during the entire design life of the bridge, which is usually 100 years design life, we need to make sure that the bridge does not encroach into any rail envelope. Okay. So this diagram here basically gives a bit more intuitive understanding of how the pre-stressed girder works. So starting from the second line here, the girder gets manufactured and stored on the precast yard. Then the concrete is still developing the strength, and also creep factor comes in. The beams are the development of the beam hog is still continuous. Going to the second line here. Then just before the wet deck concrete gets poured, it will achieve the highest hog among its serviceable life. Then once you have the wet deck concrete will then compress and cause the beam to sag. And then once the deck achieves its required strength, it becomes a composite behavior. So the super D girder composite with the deck slab structurally. Then we have the superimposed dead load. So this is the barrier, the parapet, asphalt, asphalt corrector layers, etc. So then that will then causing the beam to sag even further. Now, the bridge will then open to traffic once all the road furnitures are in place, and then we will then look at the long-term concrete creep and shrinkage and pre-stress losses throughout the design life of the bridge. Now, I'd like to mention that this is just an estimation of a single beam with a list of educated engineering assumptions based on experience. Why is that? There are a whole lot of parameters that will impact our assessment. Number one, the deck slab thickness is not deadly flat 200 mils. It's minimum 200 mils, and where required to meet the required road surface. So the deck slab can vary longitudinally as well as transversely, depending on the longitudinal fall as well as the crossfall. The superimposed dead load, again, varies across, transversely across the super T girders, because the location of your footpath, location of your trafficable asphalt, the location of your parapets, they are all in different location transversely. And then we also have the construction staging, which may vary from our assumption originally. Then this impacts your time-dependent material, the creep and shrinkage, and also the pre-stress losses. And we also got the differential temperature and the And the one of the last one is actually, based on a true project experience. When the beam deflection was, underestimated, the additional wet deck concrete may be added by the contractor. So as the construction team dumps more and more concrete, the bridge starts sagging more and more. And it becomes a bit of a snowballing effect that you don't really want to see on site. And we need to coordinate with the delivery team and make sure that we understand when was the best time to correct the finished road profile. So these are the potential parameters that may affect the deflection profile that we are trying to understand for our construction team. On the right-hand side, this is the deflection formulas for hand calculation verification. This can also be done for the continuous bridge by superposition the different deflection effects due to isolated span and continuous beam. And lastly, this is just a screenshot from AS5100 part 2. Sorry, I should have provided the screenshot here. Basically the road traffic bridge make sure that the deflection does not infringe onto the rail clearance envelope, as well as not having any sag deflection under the permanent loads, which is this last one here. We need to make sure, based on our experience, how much contingency, additional structural allowance that we need to work with our team to make sure that under permanent loads, this line does not fall below the 0. So, okay, so how can MIDAS help us? So once we understand our construction sequence, we know what we want to understand in terms of each staging, we can model this 3D effects in MIDAS program. So the beam hog deflection has been modeled in MIDAS to take consideration of the concrete creep and shrinkage, pre-stress losses, the varying deck slab, the skew of the bridge, and the pre-stress loss, and also the differential temperature effects. So on the left-hand side here is a quick example to show that the deck slab of the Hopkins Bridge actually varies significantly longitudinally and transversely, a total of 90 mils difference between the western and the eastern edge. When we model that in the design program, we actually find up to about 5 millimeters difference in the hog deflection. And on the right-hand side here, we actually get to model the hot top and cold top thermal effects as individual load cases to look at how much does it actually change due to the thermal load cases. And below that, it's an example of the ferrous integral bridge showing the beam hog at a specific construction staging. So that concludes the section that I want to sort of showcase what we do, internally for structural design. So the next topic I want to talk about is sustainability and innovation. So, we're now in an era that we don't just build roads and bridges so we can go from point A to point B. We also need to worry about the sustainability, the global warming, and all the climate changing impacts to our future generation. So at Aurecon, our corporate blueprint and the net zero 2025 policies focus on sustainability and climate change initiatives. We have a series of workshops, quarterly training sections, and regularly celebrates and recognize sustainability initiative. Now, I understand that, looking at this page, how is that relevant to bridge design? How is that relevant to level crossing? So I want to be very specific and talk about the implementation of sustainability in structural design on the project level. So basically, if we look at the mini map of the design interface, we are talking about how can we achieve sustainability, how can we satisfy durability, how can we satisfy constructability, while we provide a satisfactory outcome to the urban design team. So the Aurecon has a decarbonization methodology, and we are at the back end to deploy these strategies and methodologies onto the project level. So on this Ferris and Hopkins project, as a design team, we have carried out sustainability initiative at every single design stage. During tender and concept design stage, we actually had high-level optioneering and value for money assessment. We carry out multidisciplinary climate change workshops and set very clear target for each discipline. So for example, the climate projection data 2130 was agreed between the sustainability team, construction team, and the structures team. So for the design of the maximum shade air temperature for the bridge, we actually had to take a more conservative assumption, which incorporates the projection data 2030 instead of the minimum requirements specified in ASV 100. During detailed design, we carried out, the durability consultants carried out carbonation modeling for the structural elements to enhance resilience. The structures team provide the design for, where possible, prefabricated modularized structural elements such as Super T, precast barrier, precast concrete upstand parapets, precast retaining wall panels where possible to reduce construction and waste on site and material embodied carbon emission. In addition, we also have an agreed target for concrete mix design. So the use of supplementary cementitious material in concrete mix for several elements. So one of the examples was that we get to adopt 70% SCMN mix for the piling. And we also consider anti-carbonation coating and adjusted concrete cover for the structure to account for the long-term impacts of atmospheric carbon dioxide. So a series of workshops to discuss the actual structural cover, provision of the anti-carbon coating, and also the discussion with the procurement, the delivery team, as well as the durability team. And then the structures team also take a I think we're back on. So So structures team also take a further step, and we evaluate a list of innovative and sustainable design solutions, such as the glass fiber reinforced polymer, ultra high performance fiber reinforced concrete, and the 600 grade reinforcement. And I will talk a little bit more about the 600 grade reinforcement as a case study. And also, we also implement better stabilizing and greening product to provide a better urban design outcome. And for construction staging, we make sure that we communicate well with the construction team about to optimize our sequence and methodology. And for handover and future maintenance, for asset owners concerned, we provided detailed asset management strategy to reduce the maintenance frequencies throughout the life cycle of the asset, and carried out internal and external sustainability initiative in lessons learned for future reference. Okay, so the case study using Sense 600 reinforcement in the rail collision deflection wall. So this is pretty much basically instead of using the grid 500 reinforcement, we're now using the 600 reinforcement. This is likely to be the first time that we use the 600 grade reinforcement in the level crossing removal project. I think it's worth mentioning that big acknowledge to and recognition to the asset owner DTP. They have been very supportive and provided requirements and guidance to work with the design team, and also help us to go through the formal approval process and made it happen. So there were some specific requirements around manufacturing welding procedures, and we were able to workshop that with construction team, with the asset owner, and then get all agreed among all the parties. And the rest of the photos or the screenshots here shows that The deflection wall has been modeled in a geotechnical pole group model, calibrated for the soil spring, as well as used for the design actions for the rail collision. And on the right-hand side, the structural model in MIDAS 3D with the spring sensitivity assessment, just to make sure that we capture the dynamic behavior of the rail structure interaction behavior. And under the three models with the sensitivity assessment, we've got the output for the cantilever blade wall here to show that MIDAS is able to actually output the design actions for the full entire length. And we also used the design action of the pile to calibrate with the design piles on the left-hand side. So how does SENS 600 deliver a lower embodied carbon construction solution? So first of all, it's a code compliant product manufactured here by InfoBuild. The SENS 600 is made out of 100% recycled steel. It's used approximately 16.7% less raw material to produce the product with the same load capacity comparing to grade 500. The adoption of the SENS 600 can reduce the embodied carbon in a structure up to 39% by way of weight reduction and recycling. So this is just a couple of photos showing that they look slightly different in terms of the shape. And InfoBuild also provide us a table of conversion to show that if previously we were using the grade 500 for the structural detailing, what is the equivalent in the 600 grade reinforcement? Now, as the structural designer, we need to make sure that, every time we adopt a fancy new sustainable solution, we need to make sure that we capture all the flow-on impacts. So as the structural designer for this SENS 600, we also need to make sure that we understand what is changing between SENS 600 and the grade 500. So the SENS 600 obviously had the increased yield strength, reduced steel cross-section, which is provided in this diagram here. We have to go to check the revised calculation of the longitudinal strain and the coefficient KV. So AS5100 adopts the modified compression field theorem for shear, torsion, and moment combined design. We need to understand how does that sort of impacts on our capacity calculation and make sure that we actually revise our calculation of the angle of inclination between the concrete strut and the longitudinal tie strain. So the revised calculation of the concrete contribution and the reinforcement contribution then gets reflected and assessed accordingly to make sure that the SENS 600 is structurally adequate to resist the rail collision load as per 5100. Okay, so we're now moving to the last part of the presentation. Very quickly, everybody has been asking me, what's the difference between MIDAS Civil and NX? We'll quickly step through that. Some of the lessons learned I want to share with the team as the designer and user here is we have got some very powerful functions to turn on and off the element that we are interested in. And we also get to use the result function to filter some of these results accordingly. The next one I want to touch base is MIDAS offers various forms to work with the load combinations. I found the spreadsheet form is probably the easiest to capture all load cases in AS5100 Part 2 and then just extract and import back accordingly. The next one is MIDAS also offers, sorting out the results instead of, extracted into Excel, which, yes, you get a little bit more flexibility, but it's more time consuming. It allows you to actually filter through all your calculations within MIDAS. And we also use wood armor moment quite a bit for detailing of moment elements are subject to bending. So I've basically listed out the default setting within MIDAS, and obviously if designers require to overwrite some of these default settings, MIDAS has already provided these options. And lastly, we got the cutting diagram function, which I found, again, very useful to actually When you have a very fine model, your local per meter design action starts to become very scary and big. But it is up to the designer to actually cut a section and actually understand the average per meter design action throughout the entire length of the design, the element. Okay, so very quickly to wrap up the presentation, we talked about the API, and I just want to quickly showcase what can API function do. So API basically help us to reduce the repetitive work and help us to operate between different software, calculation program, Excel spreadsheet, etc. MIDAS has already provided a very comprehensive marketplace to showcase these API functions, and then to fast track a lot of the design process. I'll use myself as an example. I asked a lot of questions. So in 2022, MIDAS gave a presentation to all the design teams here in Melbourne. David and Connor actually gave us a very amazing presentation. I start asking questions. I start asking functions. And one of the questions that I raised was that when we look at an envelope with 100+ load combinations, how can we quickly pick up what's the governing load factor and what's the load effects? So MIDAS was able to then develop the associate API functions to enhance their performance. So Connor actually come back to me this year and said, look, Shaun, I haven't forgot about you, and this is the function that we create in under the API marketplace, and you feel free to give it a go. The program is very straightforward. Once you run the 100+ envelope, you can easily import the load combination and pick the interest element, and then select, is that a bending or shear or axle that you're interested in? Straight away, it will then convert that into a load case in the load combination with all the associate factors for EURS or SRS combination. In addition, what if you want to see factored and unfactored breakdown of each load? How does it actually governing? So MIDAS also create a load effect for the load cases. And so this is a quick showcase that you can simply select this governing load case and select the element that you're interested in and confirm the units. It will give you the breakdown of each individual load that contributes to this governing design action. Okay, so that was two very simple examples. Now I'm going to show you guys a bit of a game changer, a bit of complicated API function. So by pressing a single button, this PSC bridge model and analysis API function will be able to create a very complex, skewed, continuous bridge with longitudinal and transverse element defined with load cases, EURS, SRS, and load combinations, everything in one package by pressing one button. This is significantly more advanced than going through a manual modeling or a wizard. And then by pressing another button, it does the automatic extraction of the results and the results diagram, which enables a whole lot of function that we can now fast track, automate a lot of the design progress for bridge modeling as well as for structural detailing. And like MIDAS said, the sky is the limit. So moving forward, I think it's like the Tesla automation in driving. The machine learning needs more data. The designers needs to provide more design data to optimize our designs by streamline the bridge modeling process, identify the gaps, and then also then eventually customize the API function to achieve the automation in design with first principle verifications and responsible by the designers, of course. And that's pretty much the end of my presentation. And I'll quickly show a video that I obtained from MIDAS to show everyone that if you still have any questions after you've gone through all the online training tutorials, you can quickly log onto MIDAS website and then get help, and then click the program that you're interested in and then submit your query. And usually they will provide response within 24 hours very quickly. But look, I can't promise on their behalf, but they have been providing very amazing support during our detailed design so far. And that's it. Thanks for attending today's section. I hope everybody has learned something new and has some takeaways that you can think about after this presentation. Thank you.
Thank you, Shaun, for that insightful session. I hope everyone found valuable takeaways and gained new perspective from Shaun's expertise. It's always inspiring to learn from such an accomplished professional in our field. For our second session, Mithra Yalavarthy is a chartered bridge engineer at WSP Australia with 16 years of experience in heavy infrastructure projects, focusing on both road and rail. Registered as a professional engineer in Victoria and Queensland, Mithra's expert encompasses nonlinear analysis, extra-dose bridge, pushover analysis, and rail structure interaction, in addition to conventional structures. Her contribution include detailed engineering designs for major Australian projects like the North East Link level crossing removal in Melbourne. Mithra also played a key role in independently verifying a 150-meter span extra-dose bridge. With that introduction, it is my pleasure to hand over to Mithra, who will share her expertise and provide us with the valuable insight drawn for her extensive experience. Mithra, please take over.
Thank you, Yang. Hi, everyone. I'm Mithra Yalavarthy. I'm from WSP Australia. I'm an associate structural engineer. I mostly work on complex structural analysis. Either I design lead the structures or I am involved in complex engineering. I've done continuous super T beams over post-tension diaphragms in Northeast Link. There are 40-meter spans of super T beams on either side, combined with a post-tension diaphragm transversely. I've also done extra-dose bridge independent verification in Kachi Dargah, nonlinear analysis, geometric and material nonlinear analysis, performance-based seismic design pre-cambers, and RSI analysis, all using MIDAS Civil. I've been using MIDAS Civil from 2016. So here is an overview of the presentation of mine. We'll have how to do RSI is a simple aspect, but why to do and how to mitigate is the one which will actually take a lot of time to learn. So today I will be concentrating on both of them, apart from giving a case study on Parkdale Viaduct. So why do we need rail structure interaction analysis? We need this because we should know the distribution of longitudinal forces, and also we'll have to ensure the safety of the track systems. So the difference between road bridges and rail bridges is the rail which is connected stiffly with respect to the embankment here, as well as the bridge here. So that will actually help us act as an additional element in distributing the forces. So we need to know track structure and components before we go to RSI analysis. In rail bridges, we have a rail connected to the sleeper by means of a rail fastener. This arrangement can be sitting either in ballast or in the form of concrete. Here is an example of an MTM viaduct with ballasted track, and this is Dubai Metro with a track from plinth. In Australia, we use A60 rail sections with a height of 170 mm and a proof stress of 420 MPa and UTS of 880 MPa. It has a head, web, and foot, and this part we call toe, where the fasteners would be putting load onto the rail section. The standard rail lengths are usually between 12 to 14 meter, joined by means of fish plates like this here. In a continuous welded rail, the two parts of the section are jointed by means of a weld. So this has less impact on rail, less maintenance, reduced noise and vibration, and improved ride quality. In most of the current rail projects, in many countries, we are using continuous welded rail. This can span for up to several kilometers, and 3 to 4 kilometers is a normal range for CWR. The sleepers are usually placed at 685 mm spacing with a general track gauge here is 1600 mm in Australia. So this is a part which is of main interest to us, which will actually cause which will mainly is used in rail structure interaction analysis. So this is called an E-rail clip, and this is an S-scale clip. E-rail clip. So this is a defined elastic clip steel spring, which will produce clamping force of approximately 20 kilonewton per pair of fasteners. And the horizontal resistance generated between this clip and the rail is what will generate the friction between those two items. And that will be approximately 7 kilonewton for mainline tracks and 9 kilonewton per high-speed tracks, all dependent on clamping force. And because of the predefined clamping force of the E-rail clip, it has a predefined limited horizontal resistance. In case if we want a better fastener with better frictional forces or clamping forces, we can use for E-rail clips. Track stiffness. Track stiffness is generally based on the type of fastener being used, whether it is ballasted, frozen ballasted, or a non-ballasted track, whether it is a loaded or unloaded track, whether it is a good or moderately maintained track. Out of these three stiffnesses, the one which connects the sleeper and the ballast is the weakest. Track stiffness parameters. So in a ballasted track, the resistance will be 20 kilonewton for an unloaded track, and after that and the rail continues to slip. And for a loaded track, it will be 60 kilonewton. And this rail clip will offer a frictional resistance up to 60 kilonewtons, and after that it will simply slip. That means it will slide off. That is called rail slip. Here we can see the comparison between the different tracks of an unloaded track in ballast and unloaded track in non-ballasted track. Similarly, we can see the increase in the resistance here. So depending on the type of the track system we use, we generate this. We have different curves here. Interference of the bridge. So in a simple CWR on ground, if the temperature changes, it's with the rail expansion joint here, and if we consider all this as stiffness, after this point, there will not be any movement because these number of stiffeners, these number of rail clips will be able to resist that movement, and after that there will not be any movement, and this rail will be in a form of pure stress. Whenever we introduce a bridge in that central zone, let's go back here. So this part is called the central zone, and this part is called the expansion zone. In central zone, if we introduce a bridge, and if there is a temperature change, this will try to move this way, and because of that, there will be stresses here and there will be stresses here. So we are introducing in a CWR track, we are introducing disturbance because of our bridge. And whenever the bridge is bending, that will also cause additional deformation here whenever it is bending. So that will cause additional stresses over here. In the same way, when the bridge is sliding because of our bearings, it will slightly slide. So this will cause additional stresses as well. So I'm from Southern Program Alliance, comprising of LXRP as client, Melbourne Metro as operator, Asciona as contractor, and WSP as designer. We have successfully completed many works in Melbourne, right from initial works of Seaford and Carrum to additional works all the way currently at Newport. I've done RSI analysis for Parkdale Viaduct, which I would be sharing my lessons from here. So it is a U-trough. It is a U-trough on a ballasted track. This viaduct is around 1121 meter long viaduct with 38 spans of 27 meter and 31 meter. So it is a ballasted track, as we can see. There are two tracks which are sitting on the pier crosshead. Modeling in MIDAS Civil. So If we consider that the substructure is done in MIDAS, then the only additional item for RSI analysis is generating a rail and connecting by means of track stiffness. For nonlinear analysis, I would prefer giving center to center. So these are the only two elements which will be additional to the substructure element. The rail width embankment should be modeled for 100 meters plus and 100 meters plus to avoid any, because when we give the track changes, we don't want any interference. So for that instance, we just model 100 meters on either side of the viaduct. So this is how we do. We have the superstructure elements in our model already. So we divide them into approximately 1 meter elements because we have the track stiffness curve we gave is usually for 1 meter. So that's why we divide the superstructure into 1 meter elements. We extrude these nodes to form the rail, and we join them to form the rail element all over the top here. We use elastic links to connect them to connect rail and superstructure, and we model the embankment in a similar way. Because the ground is stiff, we gave the stiff supports here. It is usual to give in a continuous numbering way, because this RSI modeling is heavily parametric. So it is better to make this model parametric. The track stiffness, if this is a rail element and this is the superstructure, this is connected by means of a vertical spring, which is of a defined stiffness like an infinite stiffness. And when it comes to horizontal stiffness is where we give the track deformation curves. So unloaded is 2 mm over 20 mm, and we'll make it symmetric just because to take plus and minus forces. And here it is plus 60 and minus 60 over 2 mm. And after this 2 mm, the rail, we give the command that the rail can slip over here. So loads. So if the structure is located in this central zone, we can only give the temperature variation to bridge, because the temperature variation to rail anyways will not get into this. But if by any chance the bridge is located in this expansion zone, then we have to give the temperature variation to both bridge and the rail. We can use UIC or AS 5100.5. So I usually use AS 5100.2 for getting the temperature forces. In Melbourne, it usually the temperature variation of the bridge goes to about 29 and minus 18. The creep and shrinkage of superstructure can also be given as an equivalent temperature road. So the residual creep and shrinkage of the girder from the point the rail is installed is considered that difference in the strain can be converted to temperature load, and that is given as creep shrinkage load. Live load. So live load comprises of 3 effects: vertical, braking, and traction. So these are mainly project specific requirements, the type of vehicles and all. In MTM, we have a freight train of 245 LA, passenger train of 200 LA, work train of 245 LA. In ARTC viaducts, this is 300 LA. So the braking and traction forces can be evaluated by parameters advised by the authorities. In MTM, we have these parameters of traction, the length of the train, the acceleration and deceleration parameters. So it is force equal to mass into acceleration. If anything needs to be superseded by this, the tractive effort of the loco needs to be specified by the authorities. So we need to understand a little bit here. This is a single locomotive train where one engine is pulling all the wagons over here. In a double locomotive train, there are two engines back to back, and they would be pulling the whole length of the train. In a push-pull train, the engine is going to be, one engine is going to be at the back and one at the front, and they would be acting in unison to pull the train. So in MTM, they have clearly specified that 60 meters at the back and 60 meters at the front of the traction length is to be used for traction. That 60 meters is nothing but 20 meters for each locomotive. So 3 engines at the back and 3 engines at the front. So live load. How do we give live load? So in AS 5100.2, rail load can be converted into a UDL. So that is how we use UDL for vertical representation. So in case I want to load Pier 3, I would go one pier before and I would load that. And the traction force as well, I would go one pier after and I would load that. And I would repeat this for as many piers as possible so that I would not isolate any case here. So for a simple Parkdale 1000 meter plus RSI model, I have to create these many load cases for the proper iterations. The direction of travel. So the direction of travel is also important. Whenever there is an up track and down track, the forces need to be acting in unison to each other to create the worst effect. So braking on one track plus traction on one track will give the worst effect in this type of scenario, where because they share a common substructure. If they don't share a common substructure and they are independent, that is okay. But in case they share a common substructure like this, we need to consider the add-on effects here. And the load combinations. The load combinations can be taken as per UIC or AS 5100.2. So here the factor is 1, and but AS 5100 has a factor of 0.7. So either can be used. Either can be used for RSI analysis. So unloaded springs are used for temperature and creep shrinkage, and loaded springs are used for live load braking and traction. So there are two types of analysis that can be done in MIDAS. So simplified analysis comprises of adding different load cases. Like we give different load cases and we can combine them to give us a value. In complete stage analysis, what we do is we create different construction stages, and these will act in unison to give a particular combination. So this we can do only in softwares. So what is the difference between simplified and complete analysis? So if we consider that 20 kilonewton is a limit for unloaded track and 60 for the loaded track, this simplified analysis will use 60 plus 20, 80 kilonewton, which is the more the stiffness of the fastener or the fastener is, then we generate more stresses and we generate more loads. In complete analysis, what it does is it will stop the analysis at 60 kilonewton. So whenever there is a problem with the stresses not being compliant or the deformations not being compliant, then it's better we test the analysis with complete analysis. So analysis method, simplified analysis is usually what is recommended, but there will be critical cases where the maximum stresses would be there or the maximum deformations would be there. In such a case, we isolate the cases and we create complete stage analysis for those particular cases. Sometimes it will be beneficial to use that. Sometimes the number might slightly increase. So we end up with having the correct number using complete staged analysis. Range of stiffness. So this particular RSI analysis is quite sensitive. So we have to use different system stiffnesses. So upper bound stiffness of the system is used for extracting shear forces, and lower bound stiffness of the system is used for deflections and stress. So how do we do that? Upper bound stiffness have uncracked properties and upper bound stiffness of the soil. And the lower bound stiffness of the system uses the cracked concrete properties and lower bound stiffness of the soil. Unless most probable stiffness is given by geotechnical engineers, so we need to use two different stiffnesses of the soil as well. Permissible limits. So the additional tensile stress in rail is 92 MPa and additional compressive stress in rail is 72 MPa for ballasted track. For non-ballasted track, this can go to 92 MPa. So so this is in stark contrast to how much stresses we have, 420 proof stress in the rail. So the thing is, this is the stress that is the limit which is given due to the interference of the bridge. So there will be tensile stresses in the rail because of temperature and all. So this so apart from that, the rail would be experiencing this stress. So this is the limit which is tested by bridge engineers in general due to interference of the bridge. And the relative displacement between the 2 points between rail and the deck or rail and the embankment is usually 4 mm. And the absolute horizontal displacement at the abutments is 5 mm. The vertical displacement is usually 3 mm. And the fasteners need to be checked, especially for non-ballasted track, because they have the tendency to lift up, those fasteners which are adjacent to here and here. And the displacement at the top due to the vertical bending effects will be 8 mm. So here it is the cumulative effect of left and right hand side should be within 8 mm. So these are the ones for non-ballasted track. For the ballasted track, for non-ballasted track and expansion devices, UIC needs to be referred because they have different limits than these RSI results. So this is a U-trough with 27 and 31 meter spans. Here we can see the distribution of the forces of temperature and creep and shrinkage. So they're more dictated towards the abutments because I have fixed them. And this is a free pier, but the pier adjacent to that is again extracting a lot of force over here. In traction and braking as well, we can see that the abutments are attracting more force here. So this sort of estimation cannot be achieved by using empirical methods. So this is a more realistic assumption that the forces can be predicted using only RSI analysis. It takes care of soil conditions, interstructural stiffness between the piers and abutments and the embankment. So this is the main focus of RSI analysis, that we need to consider this inter stiffness between the piers. So this is the stresses that we can find for temperatures in the rail, and for traction for the traction in P1, it is actually causing compressive stress here and tensile stress here. Using a simplified analysis, we can actually see the stresses here. So for these ones which are very close to the limit, then I would actually go and check using complete staged analysis. Displacement checks. So displacement checks mostly in MTM and ARTC viaducts, the ones at the abutments are very critical. Mitigation. So mitigation is an important form because firstly, we need to try with bearing articulation. When compared to UIC, our codes stipulate more higher forces. Like UIC has 33 kilonewton meter over 30 meters, but we have almost around 40 kilonewton per meter in MTM viaducts over 60 meters. So we are checking against those same limits using higher forces. So it is very important to consider. Like how we mitigate that. The first thing is we need to check different articulations. Sometimes I check 10 or 12 articulations to find the most suitable one, which governs the track serviceability is the one which will mainly control the thing. So it's not the forces, it's the track serviceability which governs the articulations. If we can't achieve that using bearing articulations, the next thing is to change the stiffness of the system. So either we stiffen the piers up, or either we stiffen or we use the correct soil properties. And even if we can't find that, then we have to reduce the span length. This is the abutments, the spans adjoining the abutments are the one which will usually cause trouble to RSI. So reducing the span length here will also be a good mitigation criteria. In case we do not achieve compliance with after trying so many mitigations, then we need to reduce the parameters, but we need authority approval for that. The thing is, either we can consider reduced forces, because the addition forces are 0.3 to 0.4 for MTM parameters. Maybe if they can reduce them so that we can reduce the total force. So such sort of parameters, they need authority approval. And sometimes using ZLRs will be very helpful. So ZLRs are nothing but here the E-clip will be there, but there will be a frictionless material which will be isolating this these two materials not to generate any friction. So ZLRs will be useful in some cases. And the last resort is to use rail expansion joints, which I would say is the last criteria to avoid anything, because this is a heavy maintenance issue. So this is obviously a last resort to mitigation. So this analysis is heavily parametric. So sometimes I do somewhere around 50 iterations. So yes, doing 50 iterations and repetitive analysis is likely, I mean, it's difficult to do, and also it's likely to be a little error prone after doing some 40, 50 iterations. So this is where I think MIDAS Civil NX or API capabilities would be really helpful. So that's all from my end. Thank you. Over to you, Yang.
Thank you so much, Mithra, for the comprehensive and insightful presentation. I'm sure everyone gained valuable knowledge and practical insight from your extensive experience in RSI analysis. It was a privilege to learn from your expertise. We will take this opportunity to introduce a small script related to RSI. I'll show the video again. Yeah, so API plugin can be used to customize many repetitive and tedious tasks. One such example is carrying out RSI analysis on a curved bridge. The RSI wizard in MIDAS Civil can only generate straight alignments. For curves, we need to manually update all the models, which may be time consuming. As you can see up here in the wizard, we just imported an already defined wizard file. Now to speed up the process, a simple Excel API that automatically convert the alignments into curved profile for all the models can be easily created. Not only are the nodes and elements adjusted, but the local axis for nodes and elastic links are also adjusted so that they are tangential to the alignments. Tasks that could take hours can now be completed within minutes. You can see here, as soon as we pasted the map key from Civil NX to the Excel VBA sheets, both the application are connected. As we are entering the requirements parameter thereafter, we shall click on updates, and as the model as shown, and the model gets updated to the curve alignment. You can thereby look at the boundary condition at the requirement parameters as per the needs of a particular model. Then, and another example of such an API obtains a summary of LRWR forces from all the RSI models with a single click. The current report generating functionality does not provide a summary of reaction at the base of pier. Such a limitation could be easily rectified with API as being demonstrated here. These are just two examples of how APIs can increase our efficiency in daily tasks. Many more such small plugins can be created according to each organization's requirements, which will not only save time, but also increase our overall productivity. As Shaun highlighted the strength and accessibility of our tech support system, I'd like to follow up by sharing some key statistics that demonstrate the impact of our impact tickets submitted by our users. Our MIDAS support portal has been live since July 2015, and from the very beginning, we have been dedicated to providing comprehensive support to our clients. Since its launch, we have resolved over 52,000 tickets through the portal and addressed over 30,000 inquiries via direct email. On average, we handle and resolve 23 portal tickets per day. Our effort has been reflected in an impressive overall tech support rating of 4.8 out of 5. The portal has truly become our cornerstone of trust, offering engineers reliable solution, expert guidance, and valuable insight for their projects. However, while MIDAS continued to gain traction worldwide, we've observed that a few engineers in Oceania are fully utilize our MIDAS support resources. In comparison, nearly 20% of MIDAS users in South Korea engage with our tech support service and benefit from them every month, whereas in Oceania, only 5% of engineers do. We strongly encourage our engineering community here to join this global network of MIDAS users and unlock the full range of benefits that engineers around the world are already experiencing. Here are quick bullet points on the benefits of what exactly the MIDAS support portal offers. First, support policy, we ensure that the acknowledgement within 24 hours and resolution within 48 hours, providing prompt response to our users. Continuous improvement. We collect data to build a comprehensive FAQ and develop tutorials, making it easier to resolve similar queries in the future. Developer involvement. For complex issues, our developers can be directly involved, ensuring faster and more effective solutions. Future updates, development requests from users are documented and factored into future product improvement discussion, helping us continuously enhance our offerings. Now I'd like to talk about our new development in MIDAS software. As AS5100 code recently released a new amendment on 24th May this year, we are implementing the latest update, such as Amendment 2 of AS5100.5, which includes modified formulation for creep and shrinkage effects. This update is being added alongside the existing formulation to accommodate both ongoing projects that continue using the previous equation and new projects that will adopt the updated provisions. This ensures engineers are equipped to stay ahead and effectively tackle any upcoming projects with the latest standard in place. Creep and shrinkage time-dependent effects are also updated as per AS3600. And also, the compressive strength as per AS3600 is updated. In addition to existing standard vehicles that are already implemented into the software, we are adding the B-double vehicle to the database. Incorporating this B-double vehicle was possible previously as well via the user-defined option and worked very well, but this addition will increase the efficient and speed up modeling so that user can spend more time in the later tedious rating checks. The B-double vehicle widely used in Queensland has been also added to our database. Finally, I'd like to introduce one of the most significant developments we've been working on for some time. We are thrilled to unveil the enhanced capability of the General Section Designer. Traditional GSD has been a powerful tool for calculating section properties, interaction curves, moment curvatures, and stress distribution for general section shape based on reinforcement detail. With the latest update, GSD now incorporates pre-stressing as a key factor in section analysis. This means you can now evaluate both regular reinforcement and the effects of pre-stressing forces, providing a more comprehensive understanding of sectional properties and behavior. As we come to the closing part of today's session, I'd like to take a moment to reflect on our shared journey and our commitment to your success. At MIDAS IT, we are dedicated to supporting your work with innovative solutions and outstanding technical assistance. Our goal is to empower your projects and drive future innovation together. Thank you once again for Shaun and Mithra for sharing your expertise and valuable insight today. Your contribution have made this session truly impactful. Thank you so much. If you have any question, you can send us email at au.support@midasit.com. If you want to see related to tech support, you can visit our website www.support.midasuser.com.